Hello everyone. Yes. So yes, I want to start digital communication systems, and we hope you are available. And so call everyone, right? Let's try to get as much people online as possible. I know the videos will be there, but joining online is a different experience because you can talk and then ask questions. So please let that be on your mind. Right. Now I'm moving over to Tamaklu so that Tamaklu can begin. Yes.
Hi, it's good afternoon. Welcome to this stream once again. Alright, so we're going to do digital communication systems. Okay, yes, digital communication systems. I believe that we all have this book. This is the Digital Communication Fundamentals by Clark. Yeah, the man gave us a book and a solution manual. So I want us to just try some of the questions, some of the problems in the book to see how we have our calculation set. So before that, let's just go through the course. Okay, so last semester we did analog communication systems, and then we looked at we looked at how we can send information, right? So we said that, okay, if you want to send a certain information that is analog, that is continuous for every time value, we said that you modulate it, transmit it through a channel, receive it at the receiver, demodulate it, then it comes to your output wherever you want it to be. So it's something similar we're looking at here. So we're looking at something very similar. Okay, except here now we're looking at how to transmit digital information. So this is a block diagram showing the procedure. So the information source goes through encoding, encryption, multiplexing, modulation, transmitter through the channel, then receiver, then reverse process. So every process here is reverse. Demodulation, decryption, source decoding, then format, then we have our information at the output. So that's what the course is about. So we are going to look at how to transmit and receive digital signals. Okay. Yes. So if you read the introduction in this book, you'll find out that we are trying to go digital because one of the main reasons why are we choosing digital? One of the main reasons why we are going digital is because of ease of signal regeneration. Ease of signal regeneration. So you see, okay, if I have a certain signal like this, right? 0, 1, and then I send it through a channel. Okay. So let's say the signal looks like at a point, then at another point through the channel, the signal looks like this, right? Sure. Now you say, okay, if I send a very good signal that has a good signal to noise ratio, here. Since the digital has just two states, at the output, this thing will be taken back as this again because this is definitely a 0. This point is definitely a 1. You get it? So it's like because the digital has just two states, we're looking at zeros and ones basically, right? There's ease of signal regeneration. Like even though the signal will be deformed at the output, it is easier for you to just take it to a 0 or a 1 compared to a signal that is continuous over every time range. All right, please, if you have yo the screen will come. Oh, network. So Ajoba, please hold on. Right, we are trying to get the network back on.
Okay, sure. So thank you. We are now
So you
back.
can see the screen. All right, Ajoba, please, if you can see the screen, let's tell us. Okay, thank you very much. So Ajoba, I hope so. I was talking about how the signal will go through all this process to be received, and then we'll have it at our outputs. Can you please see, Ajoba? Can you please see? Then I was talking about one advantage of digital is that there is ease of signal regeneration and repeatability. There is ease of signal regeneration and repeatability. All right. Now, one disadvantage is that in digital communication systems, let's say I have a transmitter like this, right? I have a receiver like this. Majority of the resource, majority of the resource is spent to maintain sync. Like you have to make sure that okay, whatever you have here is exactly the same as what is at the receiving end. So that there'll be synchronism. So there'll be synchronization. Yes. So majority of your resource or your time is invested in trying to ensure that this synchronism happens. So that's one disadvantage, that there's allocation of significant amount of resources to synchronization. Okay, which is not so in the analog communication systems. In analog communication systems, like the transmitter and the receiver must not be identical in all respects. But for digital communication systems, you must have that resemblance. All right, so that's why we are choosing digital, and that's one disadvantage of digital. Then we came to look at classification of signals. Okay, so we came to look at classification of signals. And we say we have a first class that puts signals under deterministic or random signals. So deterministic signals, there is no uncertainty in the signal as it's being transmitted. Like every point in the signal can be determined, so it's deterministic. But for random, there is some level of uncertainty. So the word is uncertainty. Uncertainty. Yeah. Okay. Or you can say not all points, not all values of time in the signal can be determined. All right. Then now we came to also look at another one called, we saw we have periodic and non-periodic signals, right? Yes. We said that for a periodic signal, x of t is equal to x of t plus a certain constant. Okay, so there is a certain constant of repeatability at every time function. So this is how you present a periodic function mathematically. Then we came to see analog and discrete. Any question? All right, Ajuba, okay, if from a side, all right, sure. Came to see analog and discrete. So we know that analog signals are signals that are continuous for every time range or for every time value. It's okay. Discrete signals have some points, right? So this discrete means that it has values at only some specific times. All right. Then what really caught our attention, or what we spend time on the most, is something we call energy and power signal. Energy and power signal. So you must know that, you see, if I'm transmitting a signal, okay, a signal has characteristic energy. Like every signal has its own energy that it emits as it transmits within a channel. So it means that if I'm able to characterize the signal by its energy, and I don't receive that same energy at the output, then I'll know that I'm not getting the signal that I sent. That makes sense. So also, if I'm able to characterize the signal by its power, like let's say that all the signal has, let's say 100 watts, something, and other properties of power that I can characterize the signal with. and I don't receive that power at the output, then it means that probably I'm not receiving the signal that I've sent. All right. So that is what we'll be talking on. We'll be staying on for some time. That I can characterize a signal by its energy, the energy of the waveform of the signal itself, or by the power. So we have something called energy signal, and we also have something called power signal. Okay. So we derived that, since I'm sure I just want us to go to the question. So let me just write the formulas down. So we derive that energy signal has equation this: minus t over 2 to t over 2 x squared of t dt, where x of t is the energy signal, where x of t is the energy signal. Now the power, we know that power is energy over time, right? So I'll just multiply this by 1 over period from minus t over t to t over 2 s squared of t dt, where x of t is a power signal. If so, then it means that I should be able to differentiate between what an energy signal is and what a power signal is. Okay, so that will lead us to our first question we have here. The first question we have here. So the book is here, the solution manual is also here. We have them. All right, so let's start. So we are supposed to classify the following signals as energy signals or power signals. And if it's an energy signal, find its normalized power. If it's a power signal, find its normalized. If it's an energy signal, find its normalized energy. And if it's a power signal, find its normalized power. Alright. So that's what we'll be looking at. So let's take the first one. Now let's see how we can classify them easily. So how to identify an energy signal. How to identify an energy signal. So identifying energy and power signal. So the amplitude of a power signal, please note. The amplitude of a power signal is constant. Is constant from negative infinity to infinity. The amplitude of a power signal from negative infinity to infinity. All right. Now, the next thing is that energy signals have zero amplitude at time is equal to minus infinity, or at time is equal to positive infinity. So let's see how this will help us identify these signals. So first is x of t is a cos 2 pi f naught t. X of t is given by a cos 2 pi f naught t. For t is from negative infinity to positive infinity. All right. So the question is to identify if this is an energy signal or a power signal. we said that the amplitude of a power signal is constant. So this function, it has constant amplitude. Here, this is amplitude A, and this amplitude, regardless of whatever cost value here I'll put here, will be constant. So it means this is a power signal. So find its normalized power. So normalized power is given by 1 over t integral from minus t over 2 to t over 2 x squared of t dt. So that is how you use these means of identifying whether signals are energy or power signals, right? So let me put this inside. So px is 1 over t integral minus t over 2 t over 2. Put in this, so I get a squared cos squared 2 pi f naught t dt. Can factorize a out. So px is a squared over t integral minus t over 2 t over 2 cos squared. Let me make this omega naught so that makes it simpler. So cos squared omega naught dt. Right. So in doing this, we make use of some trig identities. We make use of the fact that cos squared theta is equal to 1 plus cos 2 theta all over 2. So that's what I'll use here. So here I'll get a squared over t integral minus t over 2 to t over 2 of 1 plus cos 2 omega naught all over 2. So I can bring the all over 2 outside here. dt. It's supposed to be a t here, omega naught t, so omega naught t dt. So now let me clean this side. I want to leave this one, so I wish I identify the other one, so I'm cleaning this side. So now I'm getting p of x to be equal to a squared over 2t. If I integrate 1, I'll get small t plus this cos value here. Let's say if I integrate, here, I'll get sine, right? I'll get sine 2 omega naught, right? I'm coming. Yeah, so integrate 1, I'll get t. Now this part goes to 0. Because if I integrate, I'll get sine 2 pi. So I'll get sine 2 omega naught, right? So I'll get sine 2 omega naught. Omega naught is 2 pi f. So I'll get sine times 2 pi f naught. Sine 2 pi is equal to 0. So any multiple of sine 2 pi will also give me 0. So I'll have 0 here. So this place will go to 0. So I'll be left with just t from minus t over 2 to t over 2. Px is therefore equal to a squared over 2t times, put in upper limit t over 2 minus t over 2. This place will give me t. So I get px is equal to a squared over 2t times t. That will give me a squared over 2 what? Yes. So that's how we go about it. So it was a power signal because the amplitude remains constant from negative infinity to positive infinity. So we are supposed to find its normalized power. So that's what we've done. We find normalized power. The energy signals have 0 amplitude at this. All right. Now the next is that the function is given by x of t is equal to a cos 2 pi. Let me write in. So please take note of this, okay? X of t is equal to a cos 2 pi f naught at t for a certain range of t. For t is from minus t over 2 to t over 2. And x of t is equal to 0 elsewhere. So we say that for a power signal, the amplitude remains constant from minus infinity to positive infinity. But for an energy signal, it has 0 amplitude at t is negative infinity and positive infinity. So let's see. Here, they've told us this, right? So from negative half of the period to positive half of the period, the function is defined by this. And it's 0 elsewhere, which means that x of the amplitude is 0 at negative infinity and 0 at positive infinity, which therefore makes it an energy signal. So this becomes an energy signal. This is an energy signal. And we are supposed to find the normalized energy. Integral minus t over 2 to t over 2, the function squared, a squared cos squared 2 pi f naught t dt. So I'll bring a squared out. So ex will give me, I'll bring a squared out. Then I'll have this part, right? Then I'll use the trig identity. That will give me 1 plus cos 2 theta over 2. So the over 2 come here. So I'm left with 1 plus cos 2 omega naught t dt. And we said here will go to 0. So I'll be left with just this part. So ex is therefore equal to a squared over 2 t from negative half t to half t. This will give you a squared. You get half minus half of t. That will give you t. So the answer will be a squared over 2 t. A squared over 2 t. Yeah. So a squared over 2t. That is the normalized energy. All right, so let's move on. The next signal is x of t is a x of minus at. So the next one is x of t is equal to a x of minus at for t is greater than 0, a greater than 0, t greater than 0, a greater than 0, and it is equal to 0 elsewhere. It's equal to 0 elsewhere. So here, so we see that the amplitude of the signal is supposed to be constant for it to be a power signal. An energy signal has 0 amplitude at t is equal to negative infinity or t is equal to infinity. So let's see. So this signal has this waveform at t greater than 0. Fine. Now let's see. Which means at negative infinity it will have amplitude 0. Right? So elsewhere. So it is an energy signal. So we should find its normalized energy. Now, for energy signal, you use the range given you. Okay, power signal, you use power signals. We said that what is ranging from negative infinity to positive infinity, right? So this can be a, let's say this is a power signal. But when we are choosing, we just choose a portion of it to study. That's this period here. By energy signal, you use the range they've given you. So here they told us that the time is from 0 to greater than 0. So from 0 to infinity. from 0 to infinity. Then x squared of t, so I'm having a squared. This function is like same as like having e to the power minus alpha t. So if I square this, I'll get x of minus 2 alpha t. That's like e to the power minus 2 alpha t. So that's what I've written here, dt. E of x will give me a squared from 0 to infinity x of minus 2 alpha t dt. X of minus 2 alpha t dt. Alright, so how do you differentiate exponential functions? Differentiate what is here. So if I different, so I'm coming. It's looking very clumsy. I'm coming, please. Looking very clumsy. Let me wipe the things I don't need. So if you want to differentiate an exponential, if you want to differentiate an exponential function, you just differentiate the power, and it comes to divide. You want to integrate, you differentiate and it comes to divide. So here I'm left with, I'm having a squared over a squared. E of x give me a squared. Sorry. E of x is equal to a squared. If I integrate this one, I'll get x of minus 2 alpha t over minus 2 alpha from t is equal to 0 to infinity. So this will give me a squared over minus 2 alpha x of minus 2 alpha t from 0 to infinity. So I'm having a squared minus a squared over 2 alpha. Having minus a squared over 2 alpha. Now take note that if I put in infinity here, x of negative infinity is 0, right? X of a very large negative number approaches 0, so I'll get 0 here. And if I put in 0 here, x anything to the power 0 is 1, so I'll get 1 here. So in the end, I'll get the energy to be minus a squared over 2 alpha joules, minus 8 squared over 2 alpha joule. Come in, please. Yeah, sorry. I think I've seen. So here it's supposed to be what? Upper limit minus lower limit, right? So minus lower limit. So that'll make here plus. Yeah. So a squared over 2 alpha joule. That's the answer. A squared over 2 alpha joule. That's the answer. So this is an energy signal. And I'm saying that for an energy signal, you use the range given you, right? You use the range given you. Power signal, you always use minus t over 2 to positive t over 2. Always. Energy signal, if they don't give you a range, then you use minus t over 2 to t over 2. Alright. Thank you very much. Now let's move on. Let's move on. Alright. So the last of that kind. The last of that kind is this signal here. So cos t plus 5 cos 2t. X of t is given by cos t plus 5 cos 2t from range minus infinity to infinity. So this is a power signal. Why? The amplitude will remain constant over this entire range. No matter what t is, the amplitude will still be 1 and 5. So this is a power signal. So the normalized power, as we know, is 1 over t integral minus t over t to t over t. This squared cos t plus 5 cos 2t squared dt. Alright. Now, one thing you must notice that you see, when we have to integrate this, okay, we have, let's say, x plus y all squared, right? We're supposed to get x squared plus 2xy plus y squared. Now here, if you do that, in the middle term you get, okay, let me do it so that I don't confuse us. Let me continue. So px is 1 over t integral minus t over 2 to t over 2 here. So I get cos squared t plus 2 cos, so 2 5 10, so plus 10. Sorry. Cos squared t plus 10 cos t plus 25 cos squared 2t dt. Oh, so 10 cos t cos 2t. I'm sorry, okay, I was coughing, so I didn't get to write this part at all. So now let me clean this part. We know how to identify it. Let me clean this part and you solve the question. So I'm doing px is 1 over t integral minus t over 2 to t over 2 cos t plus 5 cos 2t all squared dt. So you have 1 over t integral minus t over 2 cos squared t plus 10 cos t cos 2t plus 25 cos squared 2t dt. Now this part will always go to 0. Yes, so I'll come and get 1 over t integral minus t over 2 to t over 2 cos squared t plus 25 cos squared 2t. So if it's MCQs, then it is the same as you just squaring this and summing them. There's no need to bring the 2xy term. So that's what I was trying to say, that this term will always go to 0. It can be proven, but it always go to 0. So you just be left with squaring this and squaring this side and summing them together. Alright. So we have it like that. So now we've gone back to the something that looked like the examples we solved already. So 1 over t integral minus t over 2 cos squared t plus 1 over t integral minus t over 2 cos squared 2t dt here. Alright, beautiful. Now if you expand this using the trigger identity, you get 1 plus cos 2t, but the cos 2t go to 0, so I'll be just left with 1 over t times Ah, sorry. So I'm left with 1 over t here. So for this part, I'll get t. Please try it out. Plus this part is supposed to be a 25 here, right? It's supposed to be a 25. So it's supposed to be. So I'll get 1 over 2t times t. Then yet I'll get 25 over 2t times t. So we kindly try it. So that will give you 26 over 2. That will give you 13 watts. So you get 13 watts. So you get 13 watts. Alright. So that's it. So that's how we identify energy and power signals, and that's how we do numerical computations on them using the formulas. Sure. Now the next so the next example, we're supposed to determine. Okay, so let me go up. So from what we've done, it means we should be able to solve this question. Example 1.14 here. It's very similar to this one. Find normalized power. We can do it. Then we should also be able to find. Okay, so we should be able to do that one. All right. Another thing that you're supposed to know. Another thing you're supposed to know is that we can also quantify the energy and power signal as using their spectral functions. So I can have something called energy spectral density. Okay. So what this means is that if I'm able to quantify a certain function, let's say a certain function psi of x, in the frequency domain over a certain bandwidth. Pay attention. Oh. If I'm able to quantify a certain parameter, a certain quantity called psi x of f, okay, in the frequency domain over a certain bandwidth. So let's say this is a function. Then the area under that function will represent the energy stored in the signal. So I can therefore write the energy as, the area is integral, right? So the integral minus infinity to infinity, that function df. Hope this makes sense. So this psi x of f is what we call the energy spectral density function. This psi x of f is what we call the energy spectral density function. Sure. Yeah. Now we have something called the Pacifist Theorem. Okay. Pacifist Theorem just helps us to find a relationship between time domain and frequency domain. So Pacifist Theorem states that a function, it converts. So from Pacifist Theorem, I can convert a function in the time domain to a function in the frequency domain, right? So if I know that energy is given by integral minus infinity to infinity of x squared of t dt, is equivalent to me writing minus infinity to infinity x of f squared df. So Parseval's theorem just helps us to connect time domain functions to frequency domain functions. So comparing alpha and beta, then I can say that this implies that my psi x of f is given by capital X of f squared. All right. So this is it. So I'm saying that we can also quantify the energy of the signal in the frequency domain. Okay. So if I'm able to specify a function in the frequency domain representing the signal, then for a certain bandwidth, the area under that function will give me the energy of the signal. And we said that function is what we are calling the psi x of f, the energy spectral density. So I can find the energy of the signal if I know the energy spectral density. And I will also say that Parseval's theorem connects time domain functions to frequency domain functions. And therefore, this energy signal can be written as this. So if I compare 1 and 2, I can just say, oh, then psi x of f is given by capital X of f squared. That's all. So let's see a question like this. All right. I hope this is useful. I'm wiping it. You should have written it down already. Sure. So there's a question here. In that question, we are supposed to determine the energy spectral density of a square pulse x of t is equal to rect of t over t. This, let's see how to draw this. These functions are functions that we are not really familiar with. So let's see how they can be represented. Okay. X of t is equal to rect t over t. So this function in the time domain is drawn as this. And they give us a range, right, from minus t over 2 to t over 2. So it's just a rectangle of amplitude 1. So that's it. So the amplitude is here. So it's a rectangle of amplitude 1. So you have it like this. So if you remember very correctly, in the assignment we did, this thing was inside. Yes. So we have, so this is it. Okay. And we are supposed to change this to, we are supposed to find the energy spectral density. So we know that what? We know that energy spectral density psi x of f is given by x of f all squared. So I have to change this time domain function to the frequency domain. And Parseval's theorem is what helps us do that. So Parseval's theorem takes x of t into capital X of f. So rect of t over t in the frequency domain will give us this. So these are functions, like they are standard functions that you must know. So to give us this. So if I take this time domain function to the frequency domain, I'll get this. And this function, this is the sinc function, the SINC. So rect t over t, changing it into the frequency domain, it becomes this period will come here. Then the rect becomes the sinc function, sinc of what? Frequency. Sinc of frequency. Come in, please. Frequency times the period. So we'll have it like this. So therefore, psi x of f will be equal to this squared. It is equal to T sec of Ft squared. So the energy spectral density function will give me T squared sec squared F of T. Beautiful, 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 beautiful. So that's the first part of the question. So we are supposed to determine the energy spectral density of the square poles, which we've done, and calculate the normalized energy. We are supposed to also find the normalized energy. You know that the normalized energy is given by integral minus T over 2 to T over 2 x squared of T dt. I said this rect function is just a function with amplitude 1, right? So this is a function x of t is equal to 1. So this will give me integral minus T over 2. If I want to use this integral minus infinity to infinity psi x of f df, right, it will become complex because I will now have to differentiate sinc. So I want to work in the time domain. So I'm using the function. So the s squared of t, this is a function 1 dt. So this will give me integrate 1, I'll get small t from minus T over 2 to T over 2. So I get T over 2 minus T over 2. That will give me T joules. T joules. T joules. T joules. So this is. So this is how we make use of the energy spectral density and the energy and the Pacifist theorem all together. Okay. So the Pacifist theorem just takes a function in the time domain and converts it to another function in the frequency domain. And the area under that frequency function will give me the energy of the signal. Fantastic. And then that energy spectral density function is just given by the square of the frequency equivalence of the time domain function. Please, if you have any question, do well to ask. 30 seconds. If you have any question, please ask.
Hey, check this. Check this. You use chat. I wish you the best of. We the time. Okay. I told you when you leave me, there's nothing to forget. But I always put you back to me for you always.
Alright, no question means we can move on. So we've spoken about the energy spectral density. We've spoken about the energy spectral density. So that will help us to answer 1.12. We can also answer 1.13. Okay, no, we've not seen fully about, so we can answer 1.14. Okay, we've not spoken about autocorrelation, so let me skip this question. Skip. Sure. The next thing to talk about, let's talk about the power spectral density. So power spectral density, the power spectral density. So in the same way, I can have a certain function Jx of f, okay, and this is a certain function of a power signal in a frequency domain over a certain bandwidth, right? So if I'm able to find the area of this function. This function is what we call the power spectral density. If I'm able to find the area of this function in the frequency domain, I'll get the power. So I can therefore classify a signal based on its power spectral density. Okay, sure. So now let's move on. Let's move on and let's see something very interesting happening here. How do I get this gene of x? This gene x of f. This gene x of f is also gene x of f like this, right? This gene x of f here is a discrete sum of, just pay attention, now we say that if I find the Fourier representation of any signal, okay, let's say find the Fourier representation of any signal like this, it will be made up of what? A sum of sine waves of different amplitudes, right? This Cn here it represents the coefficient, the various amplitudes of all the sine waves that will be generated. You get it? So this Cn is called the Fourier series coefficient of the periodic signal. Okay, this is a Fourier series coefficient, and it's given by the amplitude over 2. So that's how we find the Fourier series coefficient. So now P of x, therefore, so if this is 1, this is 2, and I put 2 into 1, I'll get integral minus infinity to infinity. G of x is now this. Yes. Now, this Dirac function, which we'll talk about very soon, this Dirac function here is just showing us the position at which the spikes occur. Okay, so actually, this integral, this will just give me, so this implies that P of x is equal to sum of just the square of the Fourier series coefficient. So look here, there's a question here. There's a question here that find an expression for the average normalized power in a periodic signal in terms of its complex Fourier series coefficient. Find an expression for the average normalized power in a periodic signal in terms of its complex Fourier series coefficients. So that's the question I've answered here. That's the question I've answered here. That yes, there is a power spectral density function, and the area under that power spectral density function will give me the power of the signal. And this power spectral density function is given by this. So if I put this into the integral, this part is just showing the positions of the amplitudes of the Fourier series coefficient. So it will not feature in the final answer. So the final answer is just the integral. Just there's no df, right? There's no df here. So it's just the integral of, no, it's just the summation, right? Discrete sum from minus infinity to infinity of just the Fourier series coefficient. So this. So this is the answer for that question. So this is the power of a normalized power of a periodic signal in terms of its Fourier series coefficient. In terms of its Fourier series coefficients. Fantastic. Any question? All right, no question. Any question? Any question? No question. So let's look at our last but one question for today. So there's a question here. It's a question here. The two-sided power spectral density Jx of f. So you see how the question can be given. So they've given us Jx of f to be equal to 10 to the minus 6f squared. They said it's double-sided, don't forget. Double-sided. Double-sided means that, you see where we said the power was equal to minus infinity to infinity Jx of f df, right? It means 2 times 0 to infinity Jx of f df. So I should just integrate it from 0 to infinity and then multiply my answer by 2. That's what I mean by it's double-sided. All right. So first question is to find the normalized average power in x of t. Find normalized average power in x of t over the frequency band from 0 to 10 kilohertz. So we are supposed to find the power. That's integrate the Jx of f df from 0 to 10. And because it's double-sided, multiply by 2. So 2 integral from 0 to 10, 10 to the minus 6f squared df. So this will give me 2 integral 0 to 10, 10 to the minus 6f cubed over 3. So I've integrated, so here will not come, from 0 to 10. So I'm having what? 2 over 3 times 10 to the minus 6 f cubed from 0 to 10. So if I put in 10, I'm getting 2 over 3, 10 to the minus 6 times upper limit 10 cubed. This will give me 2 over 3 times 10 exponent minus 3 watts. Is that the answer? This number was 1.15. Okay, so it's supposed to be what? It's supposed to be 10 kilohertz, right? So 10 kilohertz. So it's supposed to be 10 kilohertz cubed. You get it? So 10 kilohertz cubed again. So it is supposed to be 2 over 3, 10 to the minus 6. So that's how we 2 over 3, 10 to the power positive 3. Alright, sure. That gives us 667 watts. So please verify this one. It was 10 kilohertz. I didn't bring the kilo when I was simplifying. Sure. So that's it. That's it. So that's how we use the power spectral density function to do some analysis. Please, I hope it makes sense. So please just use this video together with your notes. Then you realize that I'm going to touch on the things we've done by solving the questions in the book he gave us. using the solution manual so that we don't miss out on all the important things. So let's talk about something, the last thing for today. The last thing for today. Then next time we'll continue. So that's the thing for today is a Dirac delta function. So the del function. So all you must know about the del function is that if I have alright, so if I have a signal like this, right, and I multiply by the Dirac function, I'll get the value of the signal at that point. So let's say multiply by this Dirac function here. I'll get this value here. So this place will give me, like, let's say, assuming this is x of t, right? This is t naught, t1, t2. I'll get a value here that is x of t1, and I'll get here x of t2. You get it? So it's like it just picks the points on the signal. So it means that if I have an integral from minus infinity to infinity, any function multiplied by the Dirac function, shifted to a certain t0 value, it will give me the function as that point. So the Dirac function itself is del of t. But if I have del of t minus, let's say 3, it means that shift it 3 units to the right and have the Dirac function here. If I had del of t plus 4, meaning that shift it here, it will come to minus 4. So you just always equate this to 0 and find the point. Sure. So this is a Dirac function. That the integral of the product of the Dirac function at a point and a function at a point will give me that function at that point of the Dirac function. So let's see. It makes sense with the question. So let's just take a question and see. So we have a question here that use the sampling property of the unit impulse function to evaluate the following integrals. Sorry. So I'm supposed to do integral minus infinity to infinity cos 60 del t minus 3 dt. So if I compare this to this is my x of t here, this is my del t minus t naught. You said this must be equal to what? X at t naught. T naught here is what? 3. So this is equal to x at 3. This is x of t cos 60. Therefore, x at 3 is equal to what? Cos 6 times 3 cos 18. That is how we use the Dirac function in simple analysis. Let's take another example. So Dirac function So we have Dirac function t plus 4. So I'm going to integrate from minus infinity to infinity. Dirac function t plus 4 multiplying t squared plus 6t plus 1. T squared plus 6t plus 1 dt. I have it like this. So here we said this must be equal to what? X at t naught. This is t naught. T naught means equate this to 0. You get t is equal to minus 4. So find x at minus 4. This is x of t. So this is x of t. So x at minus 4 give me what? Minus 4 squared plus 6 minus 4 plus 1. 16 minus 24 plus 1. That'll give you the answer. 17 minus 24 minus 7. So the answer is this number was 1.13. So minus 7, that's the answer. And that's how you use the Dirac function to do some analysis. All right. So that's what we'll do for today. So first we spoke about why we are doing digital communication systems, right? Why we are choosing digital? Why is the world going digital now? And we saw advantages, disadvantages, and we came to look at classification of signals, and our focus was on energy and power signals. And we said that if I can quantify the energy of a signal, then it can describe that signal such that if I don't receive that same energy, then it means that's not the signal in question. And then we saw how to identify power and energy signals, how to calculate for their normalized power and energy, and then how to relate the energy spectral density to the power and energy. And then we ended with the Dirac delta function. Thank you very much. See you in class and have a wonderful afternoon.